Okay, we're going to be starting section 11.3, looking at graphs of polynomials. And in college algebra, there are three important parts of the graphs of polynomials that we're going to be looking at: the zeros, the turning points, and the end behavior. What can the equation tell us about each of these? So in this video, we're going to be looking at zeros, and in the next two videos, we're going to be looking at turning points and end behavior. Okay, the first thing we're going to do is go back and look at the definition of a zero. If I'm given a function f of x, and I look at the x values that give me an output of 0, those x values are called the zeros of the function. A polynomial function of degree n can have at most n zeros. There's a proof of this in your textbook. But basically what this is saying is, let's say I have a function f of x equals 3x to the fourth plus or minus whatever the rest of this is. If my exponent here is 4, then I can only factor this into 4 different factors that contain x's. I might have a constant out here, a, but I'm only going to have 4 factors that have x. So the most zeros I can have is 4. Okay, let's look at problem 1 here. Determine the number of distinct zeros. Well, I have my equation already factored out. This 0 is -5, this one's 4, this one's -6, this is +6, and that's -2. They're all different. There are 5 distinct zeros. On problem 2, my zeros are 2, -3, this is -3, 1, and -8. So these two are the same. So if I'm counting how many distinct zeros there are, I don't count both of them. So I have 1, 2, 3, 4 distinct zeros. And one thing I want to point out again, I think I may have skipped it, is that in all of these lessons here, I'm going to assume that all of my polynomials are written in descending order. Okay. So you don't have to worry about anything tricky there. On these next two problems, we're determining the maximum number of zeros. And the maximum number of zeros is going to be found by looking at this exponent here up front, my biggest degree. If I have a polynomial of degree 5, then I can have 5 zeros. If I have degree 3, I can have 3 zeros. Right, now we're going to be looking at how we're going to relate zeros to graphs. This problem, the directions say determine the number of real zeros and the number of imaginary zeros of each of the following. And each zero is distinct. Okay, in this graph, I'm given that the degree is 4, so I know that I can have 4 zeros. How many real zeros do I have? Well, the real zeros are my X-Intercepts, and I have 2 of them. So that means if I have 4 altogether and I have 2 real ones, there has to be 2 imaginary ones. Okay, problem 6, I have degree 3, so I have 3 zeros because they're all distinct. I'm given that in the direction, so I know I have 3 zeros. Here I only have 1 real zero, so that means the other 2 have to be imaginary. Okay, problem 7, which of the following cannot be the graph of an equation with degree 5 and why? Remember that if it has degree 5, it's going to have at most 5 zeros. So on choice A here, I have 1, 2, 3, 4, 5 zeros. Choice B, I have 1, 2, 3 zeros. And choice C, I have 1, 2, 3, 4, 5, 6 zeros. So C cannot be an equation with degree 5. Now, I want to point out that choice B is a possibility. Remember that my rule says that I can have at most. It doesn't say I have exactly 5. I have at most 5. Okay, problem 8. I'm asked to determine the real zeros. Well, I have a real zero right here, 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 and here. It's kind of hard to see those numbers, but they're at -4, -1, 2, and 6. On problem number 9, I'm given the equation but not the graph. So what I'm going to do is use a graphing calculator. Okay, here's the graph of my function, and you can see I have a 0 at 0, 4, and 5. Okay, if you look at these next few problems, 10, 11, and 12, we're asked to approximate the 0, and you can see I already have the answers written down. There's going to be a couple of different ways that you can go about doing this. One is with the graphing calculator, and the other is with a web-based program like Desmos or Algebra. And I'm going to show you how to use those in a separate video. Okay, I am trying to splice these two videos together, so what I'm about to say here may not exactly flow with what I've just said, but at least the content will be there for you. Okay, we're going to be working on figuring out the zeros for problems 10, 11, and 12, and we're going to be doing that with the GeoGebra program. And it's a free program. Desmos works very similar to it. Okay, and I'm going to start graphing. Over here toward the left, I'm going to click in this space, and I'm going to type in my equation. Y equals 2x cubed. Now, to make the cubed, I hit the exponent key on my keyboard by hitting Shift and then 6. You can see my cursor is in the position to type in the exponent of the x, so that's 3. Notice my cursor is still up there where the 3 is, so I'm going to arrow to the right to get my cursor down. And again, I use Shift 6 to get my exponent, and then plus 3. Okay, so over here on the right, you can see I've got my graph. And what I want to do is to figure out those zeros. So I come back over here next to my equation, and you see these little 3 dots. I'm going to click on that, and then click Special Points. And then over here on the left, I've got my special point. Now remember, a 0 is when your y value is 0. So you can see I have a 0 here at -7.3. That's point A. And that is the only 0 that I have. Okay, so again, a polynomial function of degree n can have at most n zeros. So look at problem 13. Below are graphs of 3 functions. We want to list the zeros and their multiplicities and state the degree of each. Okay, so I have all my zeros listed out and their multiplicities. And I'm also asked to state the degree of each function. I can find that by looking at this exponent. Now on this next function, they're not all multiplied out, but I know that when I multiply this out, I'm going to get 2x cubed and then plus something. Over here, I'm going to get 4x cubed plus something. So the degree of all three of these are 3. Okay, so the next question is, will the degree of a function always equal the number of x-intercepts? Here I have one x-intercept, here I have two x-intercepts, and here I have 3. So just because I have a degree of 3 doesn't mean I have 3 x-intercepts. So the answer to that was no. What do you notice about the multiplicity of the zeros in relation to the number of x-intercepts? Well, with this first graph, I had a multiplicity of 3, and I only had one x-intercept. Here I had a multiplicity of 2, and I had 2 intercepts, and here each has a multiplicity of 1, so I have 3 x-intercepts. So the more times I have multiplicities, or the higher my multiplicity degree is, then the fewer x-intercepts. Problem 14. Consider the graph below. Determine the zeros and their multiplicities. The zeros are where my graph crosses the x-axis, so at -3, +1, and +4. And I also want to find their multiplicities. Well, here's my equation down here. My multiplicity of -3 is 1. And here the multiplicity of 1, I can see, is 2, because that occurs twice. And the multiplicity of 4 is 1. So how many distinct zeros are there? Well, there's 3 distinct zeros. And what is the degree of the polynomial? It's going to be 4. And I can see that because I have 4 x values here in my factored form. Okay, so that's going to kind of lead us into our next big thing of talking about zeros is, how does a multiplicity affect a zero? Well, if my multiplicity is even, it's going to make my graph just touch the x-axis and then bounce back off. If the multiplicity is odd, my graph is going to cross the x-axis. So problem 15 says fill in the blank with even or odd. -4 has an odd multiplicity, and I know that because it crosses the x-axis at that point. -1 has an even multiplicity, because it just bounces off the graph and then goes back down. And 3 has an odd multiplicity because it crosses the x-axis. Problem 16, determine the real zeros of the graph and determine if their multiplicities are odd and even. The zeros, the real zeros, are at -5, 1, and 6. And the multiplicity of -5 is going to be odd. The multiplicity of 1 is going to be even, because it just touches the graph and then bounces back off. And the multiplicity of 6 is odd. Problem 17. Which of the following could be the equation of the graph? Well, if you look here at my equations, notice that I really don't care what the end part is. The only thing I'm interested in are those exponents. Here I have degree 2, degree 3, and degree 4. So if I look at how many zeros I have on here, I've got 1 0 here, and I know that its multiplicity is even. So I know that that has to have at least 2 zeros here. I have a 0 here and a 0 here. Since this is an odd multiplicity and this is an odd multiplicity, each of these could have 1 for their multiplicities. So if I count up all my zeros, There's 4. I have to have at least 4 zeros. So that means my degree has to be at least 4.